Hey everyone. So next we'll have Bill Cook from the University of Pittsburgh Medical Center and Steve Sloka from VMware. They will be talking about your Kubernetes clusters and how to decrease the downtime of your applications. Because say if you're looking at someone's website, you don't want that website to go down when you're in the middle of using it. So they'll just go through a live demo and coding session of how to go about doing this.
Cool. Thanks, Tiffany. So I'm Steve Sloka. Again, I work for VMware. My role there is I'm a maintainer of Contour. And Contour is an ingress controller for Kubernetes, as well as a CNCF project. Bill?
Yeah. Hi, everyone. Thanks for coming to our talk today. I work for the University of Pittsburgh Medical Center, specifically UPMC Enterprises, working on their patient portal. It's called My UPMC. I've been involved in the Kubernetes community since early 2015, and I've been using Spring since 2007.
All right, cool. So our talk is crossing the streams. These are rollout strategies to help keep your users happy. So again, today we're going to try and figure out ways to change your application in Kubernetes and then deal with the fallout of that, which is typically downtime for folks. So when I do think about rollout strategies with applications forgetting Kubernetes, I do think of the first thing that comes to mind is downtime. So this is some of the history of just computers, right? So Bill and I used to work together at a large enterprise, and we used to work in maintenance windows, right? We'd pick a time on a Friday night and say, hey, the system's going down. And that was the past, right? So our world now is Kubernetes and containers. But in some senses, that problem has been made harder just because of how dynamic Kubernetes can be and how fast things can be scaled. It's up and down, as well as things can churn. Nodes can go away, things can get terminated. So you've got to kind of like this makes this more of an issue in terms of dealing with this problem in your cluster. Let's do a quick background of what Kubernetes looks like, right? So this will set our stage for us to move forward. So I want to deploy a workload into Kubernetes. I'm going to create this thing called a deployment. And that deployment defines desired state in the cluster. This could be things like the image I want to run, the labels I want to apply, all that sort of information about my deployment. Behind the scenes, it creates a replica set, and its job is to manage the set of that desired state. When I want to send traffic to those pods, then I'm going to create a service in front of that, right? And the service will select those pods, and it'll go send traffic to a healthy pod that's ready to take requests. Now, when I want to change that deployment, say I want to upgrade to a new version or change some sort of, again, desired state, I'll update the deployment and we'll get a new replica set created. And then from there, what we'll do is we'll delete one of the old versions of the old replica set and we'll build a new one out. And we'll repeat that process until we come to a point where we've terminated all of the old one and we spun up the whole shebang of the new one. Now, this is kind of the crux of the problem here, right? Because when you do this deployment out of the box, your users could get downtime because we're not handling what apps are ready and what apps aren't ready. So there's a couple of things here we're going to dig into to figure out how you can have these rollouts happen and changing the cluster without your users seeing downtime. The first bit we're going to dig into is the control plane components, right? So Kubernetes has lots of different components that make up your cluster, things you don't see outside of your deployment and replica set. So here we'll talk through in this next section here. They'll walk through kind of what happens when this pod's deleted and the flow of events.
Yeah. Thanks, Steve. So first thing we're going to look at is what happens when a pod gets deleted. So this could be either via a kubectl delete pod command or as part of your deployment rollout. And it's important to note that this slide's trying to illustrate that there are two processes that are happening in parallel. So the top process, labeled number 1 here, is the control plane. So the control plane is propagating the removal of the pod's IP address from various things in the control plane, like kube proxy, ingress, core DNS, etc. And while that's happening, the kubelet, which is running on your worker node, begins the pod termination process. And the fact that these two processes are happening at the same time is actually the first scenario in which your users can experience downtime. So imagine in this case that the pod termination process that the kubelet is managing, if that completes before the pod is removed from your ingress controller or core DNS, those components can still be sending traffic to the pod's IP address, even though the pod has been terminated.
Well, yeah, and the second thing that can happen outside of the control plane type components are just if your application is handling requests, and while it's still processing requests, it receives that sig term, that termination request from Kubernetes. It's never going to send back the proper response back to your client. So this is a pretty standard thing here, but there's ways here as well that we can dig into handling these in-flight requests.
So now we're going to zoom in on that pod termination process, or part number 2 of the last graphic that we looked at. So the API server and the kubelet are working together to figure out what pods need to be terminated. The kubelet will run the pre-stop hook for the containers in your pod, if you've defined one. If not, this phase in the shutdown will be ignored. And then the kubelet will issue a sig term command. And this begins like that graceful shutdown period, where your container has a chance to clean up any resources or let things complete so that the termination ends gracefully. And assuming Kubernetes has a safety valve in place such that if your pre-stop hook and your graceful shutdown take too long, Kubernetes isn't going to let it run indefinitely. So what will happen is the kubelet will issue a sig kill command to your container and forcefully shut it down. And then at that point, the pod is terminated, and the API server is updated so that it knows the pod is no longer running in the cluster. Now, the important thing here, that pre-stop hook, along with the graceful shutdown process that gets kicked off by the sig term, that defaults to a 30-second window of time. So if the pre-stop hook and graceful shutdown exceed that, that's when the sig kill command will come into play. And you can tweak how long you have to gracefully shut down by using the termination grace period seconds attribute in your deployment YAML. And then, so this is actually how we get the second scenario in which you can get drop requests. So it's possible that after your pod receives the sig term signal, if any requests are currently in flight being handled by that pod, if your application just it doesn't trap the sig term signal appropriately and just shuts down, those requests are left high and dry and they won't complete successfully.
Right. So we've outlined 2 different ways that your applications can send back bad errors to your clients. Now we'll look at 2 different strategies to help solve this problem. So the first one, this is what Bill's going to demo, is there's an application handles this automatically by itself. Right. So we can actually change the code of our application to implement this shutdown kind of procedure. And this is great for the examples that we're talking about here, where we can actually change the code. The second example we'll look at after the demo is if you can't change that container, right? If you've got some other dependency that you're trying to run, but you still want to implement the same type of shutdown, we can look at a way to implement a sidecar pattern. But Bill's now going to do a demo of a Spring Boot app that walks you through how to actually implement this.
Yeah, thanks, Steve. If you do have us on a smaller screen, now's probably a good time to maximize it so that you can get the most out of this coding session. Otherwise, it might be a bit too small for folks. But before we get into doing an actual deployment, I just wanted to give you a quick overview of the code. So I have a /speakers endpoint that has an artificial delay via thread.sleep, just to kind of give us a chance to have in-flight requests get stuck in our container during that sig term period. And I'm just returning a hard-coded list of some of the speakers here at Spring One. So I'm running a Kubernetes cluster using kind, and at the moment I have 3 replicas of my image deployed to the cluster. So what I'm going to do is I also have a JMeter script that I can use to put load against that /speakers REST API. So I'm going to start sending requests to this, and this is just 20 users, 20 threads hitting my API concurrently. And right now you can see the thing to focus in on. There's a lot of numbers changing here on the screen, but the thing that we want to focus in on here is this error percentage column. So right now things are happy. Our users aren't experiencing any downtime. Everything's humming along. So what we'll do now is we'll simulate the need for a deployment. So let's say we want to add or change an environment variable. So I can do that in my deployment YAML, and I'll have an environment variable named downtime with a value of yep and a sad face because we don't want our users to experience downtime. So what we'll do is roll this out with a kubectl apply. We'll do a watch. And what's happening here is if you remember back to one of our earlier slides, Steve was showing basically now there's two replica sets. And the new replica set is spinning up a new pod, and as the new pods come online, the old pods will start the terminating process. And you can see, right out of the gate, we already have some errors cropping up here. And we'll let this deployment process finish. Shouldn't be too much longer.
And this is just showing out of the box, if you don't apply any kind of thing to your deployments, you're going to have, some downtimes to your applications.
Yep, that's right. Okay, so yeah, unfortunately, our deployment did cause some users to experience downtime, which not the best. So let's see if we can do a little bit better. So let's just kill this JMeter session here. I'm going to clear out those pods while I start on the next section. So in the slide portion, we talked about the two main causes of downtime for your app. So one was the Kubernetes control plane kind of lagging behind in adjusting to the fact that pod's IP address is no longer routable because it's going through its shutdown phase. So to address that, we have a pre-stop hook that we can add. So this pre-stop hook, again, that's running before your pod receives the sigterm signal. And in this case, I'm just doing a sleep command that's going to sleep for 20 seconds, just trying to give our control plane a chance to react to the dynamic nature of our Kubernetes cluster. So that takes care of problem number one. And then for problem number two, the good news is, as Java developers, as Spring Boot developers, we can take advantage of some of the goodies that came about in Spring Boot 2.3. So in Spring Boot 2.3, the Spring team introduced this idea of graceful shutdown. So it's not enabled by default. To enable it, you can see on line 1 here, there's a Spring property server.shutdown, and you set it to graceful. And what that does is that tells Spring to basically stop the servlet container from accepting any new requests, and any threads that are working on requests currently are given a chance to complete. And this support works for Tomcat, Undertow, Jetty, all the embedded servlet containers that Spring Boot supports out of the box. And it also works for traditional, thread-based servlet requests, as well as the reactive support in Spring Boot as well. Line 2 is Spring safety valve. So Spring doesn't want to wait forever for Tomcat or whatever servlet container you're running for those requests to terminate. So line 2, the Spring lifecycle timeout per shutdown phase, we're telling Spring that we're giving it a maximum amount of 20 seconds for those requests to complete. And if they don't, Spring will proceed on with its shutdown. And also good news for us, because Spring Boot is a 12-factor application, we don't have to rebuild our app to turn these things on. So I can take the exact same Docker image that I ran just a moment ago that experienced downtime, and I can apply these techniques to it to make it more resilient to application rollout. So I can set these same properties in my Kubernetes deployment YAML. And the way this works is those properties that we saw were all lowercase. So to convert them to environment variables, you put them in all caps. Any dot character would get replaced with an underscore. And any dashes, so that timeout per shutdown phase, those dashes just get wholesale removed, and you're left with a scrunched together word. But I'm using the same settings that I showed you just a moment ago in our application YAML. So let's rewind the clock and pretend that we had these settings deployed to our cluster before. And as soon as these replicas spin up, we'll try to do another deployment. And hopefully we won't upset our users by causing any downtime for them.
I think the other thing too to mention is that you've got those readiness probes, which we're seeing right now. We're waiting for.
Yes, thank you. The other big thing here in this deployment, I do have readiness and liveness probes, and I was waiting for these to go ready. That's another great addition that came about in Spring Boot 2.3. They have first class support for these Kubernetes readiness and liveness probes. So no coding on my part as just an application developer. Spring took care of this for me. Okay, so we're up and running. I'm going to start our JMeter test again. Just make sure that we got requests going through. Everything looks good. So let's again simulate another deployment. And this time, we're not going to have any downtime, hopefully. So nope, with a smiley face is what I'm going to change that to. And we'll apply our deployment and watch it go through. And this is the same process as before. We're replacing the pods that made up the old replica set with pods in the new replica set. So we're waiting for these new pods to come online. And as they do, the old replica set will get drained and we'll terminate pods in the old replica set.
Right, and the old one's coming out should have, what, a 20-second delay for that pre-stop hook, and then the Graceful shutdown will kick in the Spring Boot app.
Yes, that's right. Yeah, so they'll kind of hang in this terminating state for that 20 seconds, thanks to our pre-stop hook. Mm-hmm. And again, that's to safeguard us from the Kubernetes control plane kind of lagging behind in a dynamic nature of our deployment.
So over 1,500 requests there, and looks like there's no errors yet. So that's cool.
So far, so good.
Yeah.
Yeah. Okay. So this time, applying techniques to kind of fill the gap with where you can experience downtime. We were able to do a simple rollout, and our users didn't receive any errors. So far, so good.
Cool. So now this is the second half we talked about. So Bill just demoed how you can take an application and have it react to this Graceful shutdown. and in Kubernetes, this isn't limited to Spring Boot. It's just there's lots of niceties in there that with a couple annotations, couple lines of code, had this whole thing working. This section here I want to talk about is sort of if you can't edit that code, right? So again, I'm a maintainer on Contour, and Contour is an ingress controller for Kubernetes. And we use Envoy as our data path component. So all traffic that gets routed through the cluster routes through Envoy. When we deploy Envoy, in your cluster, at some point we have to change that version of Envoy or roll that pod or do something with it. And it's the same exact scenario where we have all of this edge traffic coming in through Envoy, and we want to have a way that we can roll those envoys and move them to new versions without having users see drop requests and that sort of thing. So this is an example of what we do in Contour today. So in Contour, we have this thing called the shutdown manager. And this is a new container we're going to add to the pod. So now we're going to have both the Envoy container running as well as the shutdown manager. And what we'll do is we'll code into the shutdown manager all of the logic and work we want to do to implement this Graceful shutdown. So here, hopefully we'll walk through this again. Afterwards, we can talk through this, and this is going to be a lot for 2 minutes. But the API will send the kubelet a terminate request saying, hey, this pod needs to terminate. Then the kubelet will also send the shutdown manager this pre-stop hook. And here we're going to hit an exec. So we're going to call a command in the shutdown manager. And what that's going to do is it's going to first tell Envoy to fail its readiness probe. It's going to make Envoy unhealthy so that no new requests get routed to Envoy. Once we've done that, Envoy will start to drain connections. So no new requests will be routed to Envoy, but we'll start to drain off those existing ones. Also, the kubelet's going to send a pre-stop hook to this /shutdown again, and so what's going to happen is it's going to block Envoy from sig terming, and the shutdown is an HTTP endpoint that the shutdown manager exposes. Now, these are both going to block. So this pre-stop hook as well as the shutdown is going to block while the shutdown manager pulls Envoy for open connections. So Envoy exposes a Prometheus endpoint, and we can go and hit that endpoint and see how many open connections there are at any given time. So basically, the shutdown manager will wait. It'll pull at a certain interval and wait for the connections to hit 0. Once it hits 0 or it finds the right time, then it will respond back to this pre-stop hook up here, and that'll signal back to the kubelet, hey, we've done enough work to get completed. All of our connections are drained. Go ahead and sig term us. So then at that point, the pod will be terminated by the kubelet. So in this way, we can add on this Graceful shutdown mechanism without having to actually, change the Envoy container that we ship out to, in the deployment. Cool.
Cool. Yeah. So just some other considerations that you might want to be aware of as you implement Graceful shutdown in your own application. So the first thing that's often tough to grapple with is how long do you wait? What should your sleep duration be so that you can wait long enough for the Kubernetes control plane to react to your pod being terminated, but not so long that your deployments take forever. And it's also important to keep that in mind when you're looking at how your app responds after the sig term signal is sent to the container. Because remember, it's the sum of how long your pre-stop hook took plus how long your app takes to respond to the sig term. And the sum of those two things is your termination grace period in seconds. So this will vary, widely cluster to cluster and app to app, but these are things that you'll have to play with to kind of find the sweet spot for your application. And another thing that plays into how long to wait, by default, Tomcat responds with a keep alive header, and that the header is set to a value of 60 seconds. So certain clients, JMeter is one in particular that respects that header, and it'll use whatever value comes back in that header to keep its connection to your API alive for that long. So unfortunately, if it's keeping a persistent connection alive, it's not relying on the Kubernetes control plane to route requests to pods that are still alive. So what can end up happening is if your sleep duration isn't long enough, your pod can go through its complete termination phase, but a client will still have a persistent connection open to your application because of the keep alive header. So just another thing to keep in mind. As far as memory and CPU usage go, you want to keep your pre-stop hook as lean and mean as possible, because any memory or CPU that pre-stop hook might consume counts against your container's resource limits in Kubernetes. So if you do something super heavy that causes your pod to run over its memory limit, it could actually result in your pod getting out of memory killed. And then lastly, debugging your pre-stop hook. Any log messages that you might have in your pre-stop hook don't come out in your normal container logs. They actually come out in Kubernetes events. So for example, if you were running a container that didn't have a shell or the sleep command in it, you're not going to be able to see that in your containers logs. They come out in Kubernetes events. And lastly, all the code that we did for the demo is available on GitHub there. There's 2 branches, a main and a final branch that shows the final state that we demoed with the Graceful shutdown. We're also linking out to the docs to describe in further detail the other lifecycle hooks that are available in Kubernetes. And then lastly, a more detailed look at Contour's Graceful shutdown support. And that's it. So thanks, everyone, for attending our session. Have a great day.
Thanks, everyone.
Thanks, Bill and Steve. That was super cool. And I hope people go and look at those resources afterward. And I'm definitely going to be looking into all this more since I haven't actually used Tomcat myself. So yeah, thanks a bunch for that.